The magnetic field force on a moving electric charge. Not only do magnetic poles exert a force on each other, where a north pole repels a north pole, but a north pole would attract a south pole, but a magnetic field will also exert a force on a moving electric charge. Now here's the key word, right here, moving. If the charge is not moving, the magnetic field does nothing to it. This is quite a difference from electric fields. They didn't care whether a charge was moving or not, they would exert a force on it. However, the magnetic field only exerts a force if the charge is moving. This is pretty unique. The force on this moving charge is related to the magnitude of the charge, how fast it's moving, and the strength of the magnetic field. But, and this is another unique point, only the portion of the magnetic field that is perpendicular to the charge's motion. That will become clearer when you take AP Physics, but for now let's just look at the equation. It's F, the force due to a magnetic field on a charge, is the charge's magnitude, Q. Its velocity, so you can clearly see here if the velocity is 0, if it's stationary, there is no force. And the component of the magnetic field that is perpendicular to the direction in which the charge is moving. Now the direction of this force on a positive charge is always perpendicular to both the direction of the charge's velocity and the magnetic field. So the only way for that force to be perpendicular to two other items, which are perpendicular to each other, remember the magnetic field component that is perpendicular to the velocity is the only thing we consider, is we have to have three dimensions again. So we use a variation of the right-hand rule which was already presented when we found the magnetic field due to a current carrying wire. In this case, instead of starting with the thumb, which is what we did earlier, remember we put the thumb in the direction of the current, we curled the fingers to the palm, and that told us the direction of the magnetic field. This time, you put your forefinger, well actually I like to use all four fingers, but I couldn't find a picture that way. Put all four fingers in the direction of the charge's motion, or the velocity. Which way is the charge going? Put your four fingers there. Then once again curl your fingers. You can see how these two fingers have curled into your palm. You should have the other finger all curling into it, and you curl it in the direction of the magnetic field. So if the velocity of the charge is going this way and you have the perpendicular magnetic field here, you curl all four of these fingers until they touch your hand, and whatever direction your thumb is pointing, that's the force on the positive charge. And once again you use the right hand rule. Now look, if the velocity of the charge is in the same direction of the magnetic field, well, you can't curl the fingers into themselves. They're already in the same direction. There is no force on the charge because there is no component of the magnetic field that is perpendicular to the velocity because it's in the same direction. We presented the case where you have a positive charge moving in a magnetic field, and that would be right here. And just to review, the velocity is to the right. The magnetic field, since it's shown by dots, are coming out of the board. It's pointing towards you. So that's nice. The magnetic field is perpendicular to the velocity, so it does exert a force on that charge. Now what if you had a negative charge moving? Well, the way we're going to handle that, we will still use the right-hand rule. We'll just pretend it's a positive charge. We'll find the direction of the force using the right-hand rule, but then at the end we will reverse the direction of the force. And on the next slide we'll show how that happens. Okay, so let's go ahead and try our right-hand rule on this. And we're just going to worry about the positive charge down here. We're going to put our hand, our four fingers, in the direction of the velocity. So the four fingers will have to point this way. Now there's two ways you can do it. You put your right hand out in front of your face, and you can either be looking at the back of your hand, or you can flip your hand around, and frankly that's a little more uncomfortable, but sadly that's what we're going to have to do in this case. You choose which side of the hand you face by which way the magnetic field is going. In this case the magnetic field is coming out of the board. The only way I can curl my fingers in the direction of the magnetic field and then hit my palm is to have my right hand facing me. Again, that's a little uncomfortable. Please try it. Your elbow's kind of off to the left. You're looking at your right hand with the thumb pointed down. I can now curl my four fingers out of the page in the direction of the magnetic field and then hit my palm with my four fingers. Now, which way is the thumb pointing? Well, it's pointing down. So that tells you the direction of the magnetic force on the positive charge. It is pointing down. So that tells you what direction this charge would be. If it comes into this magnetic field like this, it's going to feel a force pushing it down just like that. And I'll draw the line here. It'll come like this, and then eventually it'll go in a circle, but we'll talk about that later. So for the negative charge, I would have done the same process, but once I found the force down for a positive charge, that means that for a negative charge, like an electron, the force would be in the up direction. There's a lot going on this slide, so let's take it pretty slowly. We've talked earlier how the magnetic force that arises from a moving charge in a magnetic field is both perpendicular to the charge's velocity, okay, and also the magnetic field. But let's just worry about the velocity now. If I have a charge moving like this, any object frankly that's moving like this, and it has a force perpendicular to it, it will start bending it, it'll force it to go this way. It still has a force pointing towards the middle. It gets up here, it still has a force pointing towards the middle. What do we call that? That is a center-seeking force which results in centripetal motion. The charge moves in a circle. So that was covered when we did mechanics last semester, and it's the same effect here for a charge in a magnetic field. In this case, the center-seeking force is due to a magnetic field, where previously it was done by the friction of the road on your tires. If you were pulling a string and you were swirling a baseball over your head that was attached to the string, your arms gave the centripetal force. In this case, it's a magnetic field. So let's see why the force was pointing that way. I've got the velocity of an electron going this way, okay, going up when it gets into the field. The magnetic field is directed into the page, so I use the right-hand rule. Let's pretend it's a positive charge for a second. I put my four fingers in the up direction, right over here, like this, all four fingers here, and the magnetic field is out of the board, into the board. So I'm looking at the back of my hand with the four fingers pointing up to the top. I curl those four fingers into the page with the magnetic field until they touch my hand, and my thumb is pointing to the left. So that would tell you that the force on a positive charge would be to the left. But this is an electron, so the force is to the right. And wherever I go, I will always have that center-seeking force. So I will have centripetal motion due to the magnetic field, and the electron will go in a circle, and we will call that's a clockwise path. If this was a positive charge inserted, it would move in a counterclockwise direction. Let's take another example here. I have a horseshoe magnet. I'm pretty sure most of you guys have seen this at some point. A horseshoe magnet, one side is the North Pole, the other side is the South. So the magnetic field lines go from north to south. They originate on the north, they go through the south, and of course they would continue through the magnet to form a closed loop. That's what magnetic field lines do. I then have a charge, a positive charge moving to the left, and I want to find which way the magnetic field will push it. First of all, if the charge were not moving, nothing would happen. It could sit there forever. But in this case, I will take my right hand, put the four fingers in the direction of the velocity. Now, since I know I want to curl my fingers down, because that's the direction of the magnetic field, I'm looking at my right hand. The thumb actually is kind of pointing towards me. It's on my side. I curl my fingers down into the magnetic field, and the thumb is pointing directly at me or out of the page or away from the magnet. So I have the velocity going this way. So that's V. The magnetic field is going this way. And the force is coming out of the page, and you can see how it's drawn here. We would draw it for a quiz or a homework. We just put the little dot, the head of the arrow. That tells you it's coming out of the page.